Hi audience and student. This is a short lecture number 10. Before we skip the derivation of this Ridley's model of sampling effect of current mode control, and we postponed at that time the discussions about that because that will distract our attention. So we went through from the beginning to the end of this design process. Now we are going back to this one. So to have the complete our knowledge, let's go through this. So I titled the short lecture, okay? This is not short in the length, but in terms of the technical content, this is short, okay? Not easy to follow, but technical content is very precise and concise, okay? So derivation of functional block of Ridley's model. So we are talking about this, derivation of this, and the derivation of this, HES, okay? Later on, HES is creating the quadratic term, okay, in the Hepto switch frequency, which is regular double pole, LHP double pole. This is the RHP double zero. It's converted to the LHP double pole, okay, in the control to output transfer function somehow. All right, so first one is this one. So let's talk about the derivation of this. Okay, this is the PWM waveform of P current mode control. So this is the inductor current. So you are assuming this current sensing network gain is 1 unity. So it is IL. So this is the V con and V con minus V ramp is here. So at this point, switch is turned off. PWM signal is generated. Okay, but in the next period, this V con is changed to the V con prime. So this difference between V con and V con prime is V con hat. Okay, so V con hat can be considered as the input of this process. Okay, then this PWM point was here. So PWM point was here. Okay, so this is the original PWM point. The PWM point is moved to here. Okay, because of disturbance, so this can be considered the input, and this can be considered as output. This one input to output is what? Modulator gain, FM star. Okay, so you are using the geometrical construction. We are not using any equation here. Okay, so this is the expanded view of this. Okay, so this is the jump. V con hat is input, and output is this one. So this is the time domain. This is the t-axis. So this PWM point is moved here to there. But what important is this one? Time difference. Okay, change in duty ratio, increase in duty ratio, d hat ts is here. Okay, so when you construct this, okay, this is the original one, and V con prime is jumped here, and distance is V con hat. So this originally it was here, and the PWM point is moved to here. Okay, and this is the V con hat, and with this, the length of this is the same. This is a parallelogram, okay? And this is slope of this on time inductor current, and this is slope of compensation ramp, and the distance here is this one, plus A plus B is this one. Okay, it's obvious, right? So V con hat is this line segment A plus B is this one, okay? But we are interested in transfer function from here, gain from here to there, d prime. So this equation is rewritten here, down here, okay? Then this, then you get, and then you send this the other side. This is the modulator gain, FM star, okay? This is so simple, okay? Looks like this is accurate, this is correct. But somehow it's different from the other people's. Other people's had the similar claim like this. All people had their claim. If you take a look at one of their claim, everything looks okay, but they are different. Okay, they are missing something there in between. Okay, this might be okay, but something is missing in this geometrical construction. I'll explain that later. Okay, but you cannot see that here. All right, so this might be okay for some case. Understand this, okay? All right, so we finished this Fm prime derivation, and HES derivation is little bit complicated, so you need to understand the procedure, okay? There are 3 steps of deriving this, and this is the block diagram representation of small signal model. So this input is grounded. Okay? No. Oh, HES. Oh, this is the input. Okay? It's coming from input. All right? And this is this output. Okay? And this disturbance is coming from here. And we are trying to derive this transfer function. Okay? So this is the input to output. No, this is the input. This is the output. So you apply this the block diagram, Mason's gain rule here. Okay, we'll do that this later. So just apply the Mason's gain rule, this block diagram representation. Then you have first expression of S domain. This one is S domain. Everything is S. Okay, so you have first you use Mason's gain rule in S domain to have first expression. And you derive another expression, same expression but different form. Okay, so you have 2 different equations for the same thing, and you equate two expressions together. Then you solve that for the HES. Then HES will come out. Okay, that is the procedure of modeling this. Right? Try to understand this. Okay. First one is we derive 2 different expressions. One is just simply apply the Mason's gain rule here, okay? And this is the small signal model, and derive the transfer function from here to there using this the circuit equation, okay? And you set up difference equation, okay? So this is the sampling system. So this is D hat K, I hat K difference equation between this and this, okay? And difference equation, from this difference equation, you derive the G domain transfer function, very simple, okay? So this difference equation and the G domain equation, if you have G domain equation, that can be transformed to the S domain equivalent form. There is a rule, okay? Zero order hold sample and zero order hold the rule. Okay. So if you have this equation, then using 2 equations, you derive this. Okay. So this is the HES expression. This is the S domain expression. But you have this transcendental function. So you need to use some approximation, Taylor expansion, and the Taylor expansion of complex exponential. Okay. Then use some approximation called Pade's approximation. Then result will come out. Right. So then HES, originally given in this form, can be approximated. This expression, this is what? Quadratic form. With this is what? Minus quality factor. And this is the Hafter switching frequency, and it is in the numerator. So this is RHP, double zero, is coming out. Okay? So this is, there are 3 steps. This is the most important, understanding this. Okay? I explained every details in my book, but they don't read that. They hate to read that. Okay? They're not trying to understand that. Okay, but follow this. I simplified all the every details, and this is the first expression. Okay, so that transfer function is termed as HIS. Sometimes I used HIS for the current loop. Okay, but there is a slight difference. Okay, so HIS is this one, this here to there. Then you have open loop. Okay, forward gain here, and you have loop here. Okay, so loop is coming in the denominator. 1 plus loop minus, and another minus becomes positive, and this is the forward gain. So this is the first expression. Okay, it is directly written from this diagram. Extremely simple. This is the first one, and then you forget about this and dig out the second equation. Second equation is this one. So we derive this from this geometry. Okay, from the operational principle, circuit waveforms of this, we can derive another expression of this. All right. So there are two sources of disturbance. One is this current signal. The other one is this control signal. Okay. So this one is called natural response, and this one is called forced response, and this is forcing force, and this is what? This is the state disturbance. Okay. Disturbance itself is coming in the circuit component. Here, disturbance is coming in this control waveforms. So this is the disturbance is coming in. Then it goes like this, and PWM occurs here. Without this disturbance, PWM should occur at this point, and at this point, okay, should occur at this point. But with this disturbed inductor current, the disturbance is occurring here, okay? So relation between this and this is the difference equation. This is the input and this is the output. It explains how this disturbance is going to the next operational period, propagating to the next operational period. Okay, so this is called the natural response, equation number 1. And at this moment, the control voltage is jumped up. Okay, without this jumping, the PWM point was here, and the PWM point is changed to here. Okay, so this can be considered as the input of this change, and this is the output of change. Okay, so we want to write down the equation between this and this. This is the first response, and this is the natural response, and you add them together, then you have complete response, which is the sum of natural response and the forced response, which take care of disturbance from here coming together. Okay, so that can be the general solution. So suppose you have this, right? So this is the first, this natural equation. So you need to find out K1. This is the second one. You need to find out K2. Then if you find out K1, K2, then you change this to G-domain transfer function. Then if you have G-domain transfer function, then you can change this to S-domain transfer function. Automatically. There is some procedure, not automatically. Systematically, okay? There is a formula of doing this. You adapt that formula, then finally S-domain conversion will be performed. Then still you have the exponential function. Then use the Taylor series expansion of exponential function. Then you have the double pole, RHP double pole function. This is the outline of derivation, and all the derivation is graphically explained. Okay. First one is natural response. Natural response is this ILK is disturbed here, then it will propagate this, and we expand this area, then that is shown here. Okay? Suppose you have K here. This is KI. KI is here, then KI will be here. Okay, I already marked there. Okay. Okay, I have, K, not K, RI. Ri is current sensing gain. Then you have Ri here. Then you delete, right? Because they are same, and you are deleted here. Then you don't have to worry about this initially. Okay, they can cancel. But this one is different. You have okay. This one is okay, right? But when you are considering the control, the disturbance in control, you should use Ki there. Okay. Here the input is current, output is current. At there, input is control voltage, output is current feedback signal. Then you should keep Ki there. Okay. This is very easy to expanded view of this. Okay. So this is the input disturbance, and this is the output disturbance. You want to have relationship between this and this. Okay. Then from this construction, this is the Sn, and this period d hat ts, and this length is Sn times d hat ts, and this is slope of compensation lamp, and this one is Sc times dts. This is the sum of these two. Okay, and this one is this long line segment minus this short line segment. Okay, this long line segment is SF times DTS, and this short one is SE times DTS. Then you have a minus here. Okay, so this ILK is given by this, ILK plus is given by this. You find out the ratio between them, which is this. Then you define alpha with this number. Then this IL hat K plus 1 is minus alpha times IL hat K. Okay? This is extremely simple difference equation. So you have this, right? From this geometrical construction. Then you should have another one. Another one is here. Okay? So in here, this control voltage was this one, but all of a sudden it jumped here. Okay? So this is the input. This is the output. This is the difference in control voltage, and this is the difference in sensed inductor current. It has Ri here. Okay? Previously, we canceled Ri, but there is no Ri here. Okay? So you should keep this. All right, and you expand out this here. Then this green line segment is this one plus this one from this construction, and this long, this one is this one plus this one, right? And you know this TS, and you know slope. For example, this length is what? This length is this times this time. Oh, okay. This length is Sn times dts plus Sc times dts. Okay, and this length is Sf times dts plus Sc times dts. This plus this becomes this one. This plus this becomes this one. Okay, easy to see. I spent some time to color this. Okay, then this is the equation. This is the equation. Okay, and this is equation. And we have this, then this is simplified, this as this, okay? IL K plus 1 is, this is the control voltage disturbance at case period, because this current disturbance is to propagate after one switching period is passed, but this disturbance is directly changing this, because that is assumed occurred here, okay? So we have this another equation. This equation, this is equation number 2, and you are using the same variable alpha defined like this. Okay. So we obtain natural solution, and this is the first solution, and the complete solution is just the sum of them. So you have a natural solution of number 1, and the first solution of number 2, and the complete response is the sum of this. Okay. So this is the final equation, and you take the G domain transformation. Then you have K plus 1. Then you multiply that with G, okay? And with G here, no. Or G here, okay? So this is just same as the S domain transformation, but with different rule. In S domain, differentiation is S, but in G domain, time advance is G, okay? So we have G here. This is final result. Or in G domain expression, this is control to inductor current discrete time equation, G domain equation or difference equation. Okay, so this is the sampled data modeling, and from this sampled data modeling, we replace G with this E times STS. This is the switching period. Okay, I should use small s here. Okay, this is switching period. Switching period. Okay, then multiply this. This is for zero order holding equation. Then this becomes this one. Okay, so this is the final equation, S domain equation of this, which is very complicated. It has some transcendental this function. Okay, so you have two. Okay, let me finish up only this slide. Okay, this is the summary of previous step. Okay, so we went through the analysis of natural response and analysis of forced response, and we obtained the complete response, and we obtained the S domain expression of this using this G domain to S domain conversion process. Okay, so this is the second equation. You first derive the first equation from the block diagram. Differentiation, okay, is shown here. Okay, so summary of derivation. We did this directly. We wrote down here, and from this control waveforms, we derive this equation, and we equate them together here. Okay, so HIS expression is shown here. HI expression is this one, and this is this one. They are the same, right? They are the same equation. Then here we have, and this can be solved easily. Then we equate this, and this, and find out this, dig out this HES. Then from this equation, HES can be evaluated, extracted. Then HES is transformed to the non-transcendental function using the Taylor series expansion and the Pade approximation. Okay? Right? So we'll cover that in the Thursday for the final stage of this. Okay? Then we'll understand where this comes from. Okay? This is very rigorous. Okay? It looks tricky, but this is rigorous. Okay? So Ridley summarized this, but prior to him, many people played with this. Okay? There are many other peoples who played with this and derived the G domain expression, but the Ridley is the first guy. He derived everything here in S domain and transformed the simple equation, second order equation. Maybe that is the huge contribution. Okay? Other people, they used G domain expression and power stage modeled in G domain, and they got trouble. Okay, so complicated. All right. So punchline here is combining with the existing S domain model with S domain representation of sampling effect, which is derived from the sampled data analysis technique. Okay, that is the essence of Ridley's contribution to this work. Okay, all right. Okay. This is the continuation of previous part of lecture. This is lecture 10, right? Short lecture 10. And let me review this. Right? So in the previous lecture slide, we derived two different equations for the HIS. HIS is transfer function from this control voltage to this inductor current. So that was HIS. And maybe I need one clarification. Maybe I got mixed with this TIS and HIS. Okay, let me clarify this. HI is transfer function from this control voltage to inductor current, and the TI is current loop. Okay, so TI is product of RI, HES, and FM star, and transfer function from duty ratio to inductor current. Okay, so that is TIS, and HIS is simply transfer function from here to there. It's not directly related with it. It is related with this, but they are different. I think I made some mistake. I got confused with the two things, but let's differentiate them clearly from now. So this HIS transfer function from this control voltage to inductor current. Then we have this forward path, which is this times this duty ratio to inductor current transfer function divided by 1 plus this current loop. Okay, so this one. This is the one equation. This is the first HIS expression. Okay, which is extremely simple. You can immediately written from this block diagram representation of small signal model, right? And we have another equation. So we derived one equation, and we derived another expression for the HIS. Okay, that was a little bit difficult, but it is summarized here. So you are talking about, we mentioned two different solutions. One is natural solution, and the other is forced solution. Okay, so this is the disturbance in the inductor current, and this perturbation in inductor current is propagating like this. So this is the original PWM point, and this is the new PWM point due to the disturbed inductor current, and this is a time difference. Somehow we want to have a relationship from here to there. Okay, it's the natural solution, and using this geometry, we used this D prime D hat TS, and the slope of this sense waveforms or this RAM signal or control voltage. And so we derive relationship between this and this. Okay, that was the natural solution, and the other one was the forced solution. Forcing function is perturbation in this control voltage. So control voltage assumed to jump at this point, and the perturbation is changing this PWM point, and this is the result of this perturbation, propagation of this perturbation. So we derive transfer function from here to there. Okay, to there. The step is very similar to this. We use the geometrical construction of this. We used this time interval and the slope of various waveforms associated with this PWM function. So we have a natural solution and we have forced solution. We summed them together. That is the complete solution. Okay, we derived that, and based on that, we found out the difference equation of this system. Okay, then this difference equation is transformed to the G-domain equation, and the G-domain equation is transformed to S-domain equivalent. Okay, so the transformation from the G-domain to S-domain is well known, and there is a formula, sampling and zero order holder. Okay, this is the formula, so we use that, and the result of that is this. Okay, so this is the S-domain equation, but it has this exponential function. Okay, anyway, this is the S-domain equation. So we have one equation, we have another equation, they are same thing. Okay, so we equate two equations here. Okay, let me put this way. So this is this one, HIS, derived from this block diagram representation, and this is the HIS, derived from the geometric construction of PWM waveforms. So they are same thing, okay, because they are the same transfer function from the control voltage to inductor current. So we have this relationship, okay, and there is HES. Then using this equation, we can solve another equation for HES. That is our purpose. We want to identify the the expression for HES. That is the purpose of this. Okay, so this is the beginning of this, the extracting this expression, and we need some simplification. And this is FM star times this one. FM star is this one, based on the Ridley's PWM modulator gain for current mode control. This is the Ridley's expression for FM star, and this is the expression of this one. So you can derive this, or you can understand this, and maybe you may refer to my book or Ridley's dissertation. Then you come up with this. Okay, so this one is modified to this. Okay, and this alpha is given by this. Okay, okay. Let me repeat this. This part is FM star, and this part is derivation to output transfer function. This is the sum of this, and that is simplified using this alpha parameter. We defined this alpha. Okay, so this is the some propagating constant. Okay, so this is very important. And then we know we simplify this because this is transformed to this. It is same as this, right? No. This whole thing is the same as this. Then this blue part went here is depressed with this one, this one. Then we have this expression. Then this can be solved for this. Okay. So you need some simple algebraic. Okay. Then the HES is given by this, right? So there is a problem in the textbook to prove this. Proving this is not easy. Okay. It requires some labor. Okay. But it is possible to derive this. So this is the S domain equation. Still you have a problem. This should be replaced with something we know, polynomial of S. This is some transcendental function of this one. Okay, exponential function. Complex exponential function, because S is sigma plus j omega in general. So this is the complex exponential function. And then we want to replace this with the polynomial equation. All right. So this is the trick. So ETSTS is this one, and you divide it 2. Okay. So this is the plus, and this is the minus. It goes to the upstairs. Then it becomes this. Then it becomes this. Okay. You split into 2. One is positive. One is negative. Then you have this. Okay. There is a relationship between 2 pi omega st. Okay. 2 omega st is 2 pi. Then using the relationship, you have this. And this is the exponential function of S. Then you have this, the Taylor series. Okay. So this is accurate when x is much smaller than unity. Then it is expanded like this. Okay. This trick, I think this is some simple trick, is called Pade approximation. Pade, I don't know who this guy is. Okay. They have something here. Pade, I don't know. Pade approximation is this one. Okay. So we use this, and during this process, this term appears, and you calculate this. Then that is about 5. Then you replace 5 with this 4. You can put this equation in this nice form, right? So this is about 20% error. Maybe rather crude approximation. Okay. Then you have this nice form. Okay. So this is the trick, the Ridley did. Okay. But that is acceptable. All right. So final expression of this one is this approximated expression. Then you have this, right? So this is original equation of HES. You have this, and this is converted with this. and you have this one in the denominator, so which is this, and -1, you simplify this, then this is simplified, this is the exact expression, then it converted with this, and this is here QG is -2 divided pi. So it has negative quality factor. So this is a double 0, but 0 is appearing in the right half plane. Okay, and this is omega n is this one. Okay, this is the half the switching frequency, half the switching frequency. Okay, this is very critical. Otherwise, this will be not this simple. Okay, with this approximation, he was possible to put this in nice form, all right? And he was talking about half the switching frequency, something like that, with this. Okay, all right. Okay, so this is the procedure summarized in his dissertation. I think we had about 9 or 10 pages of derivation. Okay, I spent some time to summarize this. Okay? First time, it is not easy to understand what he was intended to say. Okay, so this is his message. So this is the final form of this model. We went through this previously, so this is the second visit. Okay, this model we visit, and FM star is this one, and HES here is this one, RH00. Okay, so sometimes you want to simulate this. Okay, if you use some program like MATLAB, you can use this minus sign here. But if you use circuit model like ORCAD, PSIM, you need to have some simple circuit model for this. This is the model. Okay, so if you find the transfer function, this is G2, this is G1, G2 divided by G1 will be this form. Okay, with negative sign in front of this. Okay, for the PSIM simulation or some circuit simulator, it's not easy to implement this. Okay, then use this. Okay, that has the negative resistance. So most simulator accept the -R negative resistance. Then just use simple this. This is the simple circuit with ideal OPM and the passive circuit component. And remember, you have minus sign in front of this. Okay, so this is the final form of this model, and we know somehow this HES smears into the dynamics of this system, and later on it emerges as the double pole in the transfer function from here to there at the half the switching frequency with positive quality factor. So this RHP0 in here, somehow it becomes LHP pole, double pole, in the control to output transfer function. Okay, that is the highlight of this modeling. Okay, we started from this control to inductor current transfer function, and later on this guy is smeared into, propagated into the control to output transfer function in the form of LHP 00 occurring at the half the switching frequency. Okay, so this is the old one. We went through this. Okay, just I'm reminding this HES and FM star is all the same for all the PWM converters, and this KF, KR. This is the feed-forward transfer function from input voltage to duty ratio. This is from the out voltage to duty ratio. So they are different. It changes this buck converter, boost converter, and the boost converter, and this older expression is different from the result of the another guy, Dongten. Okay, so there are two different models. There are many others, but two of them is very popular. So one group of school or institute, they use this one, including me, graduate from Virginia Tech. Okay, and the people associate with Caltech, they use another model, but they are similar, but they are different. So I don't know which one is more accurate, but As I said several times, finding out the exactness of that model is not important now. Okay, you can take any of them because they don't matter that much. They don't matter that much in the final result. Okay, that was very tricky. Maybe some guy is spending 20 years to figure this out. He's still struggling. Okay, I did once and I gave up. Okay, that's not important. Right? Okay, this is the end of short lecture 10.